Alrighty, my name is David Hoyt, and in this video I'll be reviewing the structure and function of the nucleus. Before I dive too deep into that, I think we should hear from an actual physicist.
They may have the appearance of riches, but beneath the clothes we find a man, and beneath the man we find his nucleus. Nucleus? Yes.
If that doesn't resonate with you, I don't know what will. So actually, just one slight correction. Beneath the man, we find 7 times 10 to the 27th nuclei. So we're composed of tons and tons of atoms. And the nucleus is the massive center of the atom. So it contains the vast majority of the mass in the protons and the neutrons. So protons are positively charged nucleons, and neutrons are neutrally charged nucleons, so they have no charge. And we differentiate between different elements, different atoms, by the number of protons in that element. So for instance, carbon will always have 6 protons, regardless of how many electrons or neutrons it has. So as we look at the periodic table of elements, we see different notations that tell us about each of those elements. First, X, that represents the 2-letter name given to an element. Z is the atomic number, which is the number of protons. So those two things will always be the same for an individual element. And then A represents the mass number, so that's the protons plus the neutrons. So to determine the number of neutrons, we subtract the atomic number from the mass number. So just as a practice, look at this practice problem with boron 11. So boron always has 5 protons. So just in your head, if it has 5 protons, how many neutrons would it have? Hopefully you get 6. So yeah, you just subtract the atomic number from the mass number to get that. In terms of size, the nucleus is obviously incredibly tiny. To figure out the size of an individual nucleus, we calculate that by taking the radius of an individual nucleon and then multiplying that by the mass number, so the total number of nucleons raised to the 1/3. And then to get the volume, it's just the standard volume equation there that we use the radius that we calculated there. So because these are so small, it requires a strong force to hold those charged particles together, because you would think all of those positively charged protons would be pushing apart, which we'll get into more depth later. But just know that the nuclear force is what resists the pulling apart and the compaction of those nucleons. So continuing on with size, mass is an important aspect of the nucleus. We calculate mass based on atomic mass units, and we take carbon-12 as it's the most abundant element that we have, and divide that by 12 because we know there are 12 nucleons in carbon-12. So that gives us an estimate of the mass of one individual nucleon, which comes out to be 1.6605 times 10 to the negative 27 kilograms. So tiny, tiny. But still, protons are 1,836 times more massive than electrons. So that's evidenced here, or portrayed here, with that bowling ball versus the penny. So a proton is represented by the bowling ball, an electron is represented by the penny. So a proton is much more massive than an electron, and neutrons are even slightly more massive than protons. An isotope is an element with the same number of protons but differing number of neutrons. So just like how carbon-12 is the most abundant form or isotope of carbon that we have, and it has 6 neutrons. But there could also be carbon-11 or carbon-13, which would have 5 or 7 neutrons respectively. So as you look at this chart here, you'll see that the mass of an individual proton and neutron is actually heavier than just 1 AMU, which you would think. So if you had 6 protons and 6 neutrons, you would think that would come out to being more than 12 AMU. However, some of that mass is actually converted to energy, which we learned from Einstein's E=mc² equation, the energy that's used to hold these nucleons together it comes from the mass. So mass can be converted into energy and measured in units of energy. So carbon-12 weighs less than mass of 6 protons and 6 neutrons because it loses some of its mass to nuclear energy. And then we see here as well that the electrons are incredibly, greatly smaller than either of the nucleons. So nuclear energy is obviously a very important topic today. And we would think that, as I was saying earlier, that protons would have a strong repulsive force. Electromagnetic force increases as distances decrease. So you'd think that having those protons so close together would have incredible force, a repulsive force, which is true. However, we have the weak and strong nuclear forces that overcome the electromagnetic force in close proximity. So these forces together act like a glue that holds together all of the nucleons and resists compression. So the strong nuclear force in close proximity is 100 times greater than the repulsive electromagnetic force. And it's responsible for alpha decay, whereas the weak nuclear force is responsible for beta decay. And because these forces are so strong, we can harness them by forcing these decays and then capturing that energy. So that's where nuclear reactors and nuclear bombs come in. So electric repulsion of protons strains the nucleus as portrayed here, but then these strong nuclear and weak nuclear forces are the glue that hold the nucleus together. So kind of an interesting ratio we see here between protons and neutrons in a nucleus. At low masses, we see that those numbers are equal most of the time. So for instance, with carbon-12, there's 6 protons, 6 neutrons. But as we go up this chart here, we see that there's an increasing number of neutrons per proton. So the ratio it favors neutrons more as the mass increases. And that's because as you add more and more protons in, the electromagnetic force will get greater and greater. So the Coulomb force increases. But by spreading those protons out, by increasing the number of neutrons in the nucleus, we spread out the protons a little bit such that the Coulomb force is decreased while the strong and weak nuclear forces are still gluing it all together. So it just makes it more energetically favorable. So in addition to the larger number of neutrons that we see, that trend, there's also a trend of just having a wider variety of stable nuclei at larger masses. So down here towards the bottom, we see a very narrow range, but yeah, up here, that range increases a lot. So yeah, that sums up the nucleus. Thanks for watching.